Good morning. Welcome to the seminar on control systems. The control systems can be well studied by using a tool called as MATLAB, but before that we will need to see some theory related to control systems so that we can utilize the MATLAB tool to the best utility. Control systems is a subject. It is related to industrial control, automation, it is related to motor control, it is related to electrical engineering, it is related to machines, etc. It is a broad subject. However, the control system involves some concepts which are to be well understood before taking on some manipulations using numerical tools, some numerical methods. The numerical methods involve the analysis of some computations that have some parameters being manipulated. The parameters are not easy to be manipulated. They involve some calculators, they involve some computing methods. To use the calculators and computing methods, using a computer, we need to use a software. The software should be well sophisticated. It should support computations, it should support data extraction, it should support data manipulation, it should support cross-platform. Hence, we need to use a very good tool like MATLAB. Now we will see some control system concepts. Control system has got some fundamentals. The fundamentals should be well understood. These are the fundamentals. They need Laplace transform. Laplace transform is a mathematical numerical method which is going to convert some polynomial into S domain. There is a domain called as the S domain in numerical methods that is well needed for some plots. We have some graphs, we have some XY coordinates system, but this XY coordinate system is not like a graphical system. This is like a polar system. For the polar system, we need to understand the S domain so that these plots become easier in the S domain. Then we have the stability circles. Stability defines how the numerical analysis derived from a system is going to affect its stability by change of some parameters in the stability circle. The stability circle plots the parameters such that anything within the stability circle or in the outreach of the stability circle is going to affect the entire system. Then we have transfer functions. Transfer functions are functions that are relating a particular domain to another domain. There is a change of two domains in these systems. Transfer systems and transfer functions have these relations to the domain, related technologies. Then we have signal flow graphs. Signal flow graphs indicate when a system is subject to particular type of signal, what happens to this signal and how the system is going to behave with this signal. This can be seen directly in a measurement instrument, but we can also derive such system behavior when it comes to the signal with mathematical analysis. So the control system gives a broad provision for mathematical analysis using numerical methods. The numerical methods can be interpolation methods, it can be computational method, or it can also be hand-derived. But it is very difficult to be hand-derived for every system or each polynomial function. Hence, we need to use advanced computing systems like MATLAB or Xylab. We have an interesting part which is the backbone of the control system, which is called as a Nyquist plot. The Nyquist plot are definitely the polar plots. We have the polar plots like any of the plots which are going to define the stability of the system as well as the two dimensions for this particular system in a very good graphical format. The polar plots define the relative stability, and they have got the M and N circles. M and N are parameters which are going to define based on the poles which are obtained in the polynomial equation. The equation may represent a numerator and a denominator with the polynomials, not just the values. It is not a decimal but the polynomial equation wherein a particular coefficient is substituted with some value. It gives a value which is going to be directly plotted in that circle. And this particular plot of a value in a circle cannot be done hand derived one by one. It will take some hours, but the method can plot the value and it can give us a very good graph in terms of a polar plot. Then we have the root locus and board analysis. Both plots are they are plot of gain of a particular function. We have a system which is going to give some gain. Gain means what is being effectively given by the system for the input signal and what we derive in the output. The gain is plotted by means of the board plot or board analysis. How the gain varies with frequency is termed as a frequency response. The signal incoming is not definitely one frequency. It is going to vary in frequency, or even signal combined with noise has got many frequencies. Hence, the signal along with noise has got many frequencies, but the gain is going to be determined the signal output, which is going to be either noisy, or it may say to the external person or the designer that it needs a filter for the signal. Otherwise, the output of the signal system will be extremely noisy. So these are some of the concepts, theoretical, which can be derived with numerical methods and mathematical analysis. It can be hand derived. However, only the hand derivation is going to give us some good understanding the first attempt, but the next attempt will be a computational analysis tool, advanced tool like Xylab or Matrix products. We will start into the control systems. Some practical examples of the earlier control systems used. In earlier systems of aeronautical engineering, industrial engineering, mechanical engineering, electrical engineering, control systems did not have a feedback, but the technician is going to monitor what is happening for the parameters every now and then. One simple example of a design of a hovercraft. Hovercraft is a very good engine. It is a propeller. It can facilitate the travel of a person from one place to another. But the hovercraft contains just an electrical machine which was used for propelling the particular engine, and then the hovercraft carried the person from one place to another. It did not have a control system. It had a start-restart switching system instead of a control system. So this is like a non-control system product which was still in practice in the early days. Shown is another example of a non-control system. This was a small prototype missile rocket which was designed with the help of gravitational theoretical derivation with mathematics, as well as the mechanical structural analysis from mathematics. So these are simple examples of mathematical calculations that led to many inventions. However, the control system is not just like the earlier inventions. The control system is a proper feedback analysis system which involves computation, simulation, and the practical monitoring of the entire system. This is required if some errors occur in the system. The errors should not be repeated. Even though the errors repeat due to the cost constraints or the manufacturing defects, the error must be having some replaceable systems or add-ons, the additional systems that can correct the errors in some other manner, either through a filtering or through a discretion method. Control system involves the design of three kind of controllers. When you say control systems, the output of the control system or the product of a subject called a control system will be a controller. The controller is divided into many types, namely the feedback control, which involves measurement, comparison, computation and correction. It also involves the integral control. Integral control, there the error becomes almost nil. It involves the proportional control. Proportional control takes the gain into account. The gain of the system is very important for a proportional control. Then it also involves a derivative control. A derivative control is a particular noise filtering system wherein the input noise will be nulled to zero. It is a derivative control system which is very unique and it is very sharp in giving it the output. And we have the multivariable control system which takes into account the cascade control, then the ratio control, feed-forward control. These are some controls that are different from a feedback control. Multivariable control is a system which contains a lot of parameters that can be adjusted simultaneously, but they have to be monitored, and we cannot say that the system can give us the entire feedback that is going to be utilized in correcting the system automatically. This is not possible in a multivariable system, but the feed-forward control is one such of multivariable control which is being utilized in industries for various mechanical applications as well as electrical automatic control applications. Shown is best system for electrical automation system, wherein we can see some feedback loop which has got sensor drivers, then task scheduling, then file manager which can document that particular task, then error handling and graphic routines. Error handling, graphic routines are very important for display on screen so that the technician who handles the control system comes to know whether there is a system in process or there is a stoppage of the system process. This is the best example, easiest example of a control system process. Control systems, they have got a broad classification of the systems based on differential equations. Differential equations are part of numerical methods and mathematical analysis. The differential equations have some linear constant coefficients. These linear constant coefficients are manipulated again and again to derive a fundamental value which is very important for deciding the threshold for a particular system. The threshold will decide whether the system can exceed that particular value or the system should be retained within that particular value. This is being decided by the constant coefficient which will yield to a value from the differential equations. To study the transfer function, a simple RC or RLC circuit is enough to determine the transfer function of the particular circuit. The input and output can be manipulated just with the transfer function. So this is called as a transfer function helping the output analysis of a particular input system. A simple RLC circuit in electrical terms, a RC circuit or a LC circuit is enough for studying the transfer function of a system. However, the advanced transfer function analysis are for operation amplifiers. Amplifiers are used in control systems extensively. We call them as integrated systems of amplifiers, linear amplifiers. They are not nonlinear as in some optical systems or in microwave systems wherein we have a nonlinear operation. But in the control system, industry control, we use some linear integrated operational amplifiers which are mainly based on the system coefficients as well as the gain formula. The transfer function of the particular individual amplifier unit is very important for integrating a system with multitude of subsystems. Shown is a particular example of a signal flow graph. You can see the signal flow graph. This signal flow graph is not very vital when we take a RLC circuit or RLC circuit. It is not of significance. But if we use linear integrated operational amplifier circuit interconnected, then the signal flow graph is very essential in determining what happens to the entire system. It has got many nodes. We define the nodes of a particular system. A control system integrated with a lot of units have got multiple nodes. Then we have the start node and the end node. Then we have the feedback system in the middle. So these nodes are very vital in translating a particular path, which is going to be essential as the quickest path, which is determining the signal output in the quickest time. The main purpose of such analysis is how long the system takes to give an output to the input signal, and this is called as the transient analysis. The transient analysis cannot be done for the entire system as a whole. Transient analysis might have been done for a single unit or an amplifier or a particular circuit, RLC circuit, RC circuit. However, we cannot do the transient analysis for entire circuit by monitoring each unit, but we can say that there is a path analysis. The path is being traced as a signal flow, and this signal flow graph is going to give us, in a nutshell, the transient analysis. We cannot say that is the transient analysis value which one can analyze, but we can say that this is the easiest path with which the signal will be very stable. And if this path is being cut or hurted in some accidents or errors, then there will be an alternate path for the particular system with which the system will be still functioning. This is the greatest achievement of a control system. Even if one path loses its credibility, the entire credit of the control system is not lost. The control system still functions, and this is wanted by us as the designer of a control system. I spoke to you about the feedback and non-feedback systems. Just now we saw non-feedback examples, diagrammatic examples of some hovercraft and rocket missile propulsion. However, the feedback control systems are used in industries with a lot of regulations, and the purpose of such feedback control system is to examine the extent of system stability. The system has to be stable for long duration. It may be hours or days. Hence, we need to examine the degree of the stability. Then, the steady state performance. After some hours, the environmental conditions may change for a system. The system may be in an ambient temperature at the daytime. It may be involving the coolant, or the system may be in a very low temperature in the night time. It may not involve some coolant or a cooling system. Hence, the steady state performance of system with respect to environmental conditions, with respect to some changing noise input signals, is very important. Then the transient response, just now I explained about the transient response for the RC circuit. The RC circuit is needed for determining the transient response of a simple circuit. However, the transient response of the entire system is very vital, and it cannot be analyzed stage by stage. However, the multiplicity of the same kind of units is very vital in analyzing transient response of the system. We also have the signal flow graphs, as I said, for determining the path which gives us the quickest signal with the input signal in operation. And we also have some related parameter called as the bandwidth, which is not vital for the entire system, but it is involved in systems where amplifiers are in practice. When there is an amplifier in a system in the middle, then it involves the analysis of the bandwidth. The bandwidth and the gain product is very vital for some amplifiers, which is not going to be discussed in the control system for industrial automation. However, it is going to be vital for some amplifiers and radio operation, which is not of concern now. When you take about the control system, I saw there is a Nyquist plot. Nyquist plot can be of many types. It can be a singularity plot, and it is a real and complex plane plot. It can also give us the Nyquist polar plot. So, as I said, it is a singularity plot. It is a real or complex plane plot, or it can also be a polar plot. The Nyquist plot leads to a Nyquist path, just like what we see as contours. A contour is a diagrammatic representation of the various heights in a particular area. The heights are with respect to the distance, and the contour connects the regions of the same height in a particular diagrammatic plot. Similarly, we can see the Nyquist path, which is going to connect the parameters of certain values, set values, where they will operate as a constant and they will operate in a stable manner. This is given by the Nyquist path. Nyquist path is derived from various Nyquist plots. It is not just one Nyquist plot which is going to give us a Nyquist path. For this analysis, we need computing system analysis using the computational tools like MATLAB. We don't need a computational tool like MATLAB for just one Nyquist plot, which can be derived from our brain or numerical calculations manually. So Nyquist path and the stability circles are complicated, and they are derived from the computational analysis, and they give rise to what is called as a stability circle. Stability circle, they can indicate what will happen to a particular value of a signal due to the system stability. Whether the system may reject the signal or accept the signal is derived from the stability circle, which is very difficult unless and until there is a practical data comparable to the theoretically observed values. This is one such circle which is shown. The stability circle plot from the computer will look like this, and this is more or less giving us an overview how the path traced by will be graphically given to us. We have another analysis graph, which I call as board analysis. Board analysis is widely used for analyzing a gain of a system. Gain of a system is very important for the signal value at the output. The signal value of the input may be noisy, it may be low, it may even be not sufficient to drive a particular system component. For example, motor or an indicator system or an alarm system, the signal input may not be sufficient to drive a particular component of the system, but the signal value of the output of a particular control system is very important in deciding how the components are being driven as an indication to the technicians, or a filer up system, or an alarm system, or even a monitoring system, the output user. So a board analysis involves the gain analysis of a particular system. Normally, the board analysis is done by means of a polar frequency, not like the frequency which we saw in radio applications. In radio applications, we use the frequencies from hertz. We say it is a linear frequency, that is, the frequency may vary from 20 hertz to 20 kilohertz, or it may vary from 20 kilohertz to 100 kilohertz. It may vary from 100 kilohertz to 100 megahertz in various AM, FM, or audio applications. However, the board analysis is not for such a radio analysis of frequencies, but it is for industry control, wherein the particular system has to decide whether to pass the noise frequency, or it may consider the frequency input to the system as a pulse frequency and pass it to the output. So this is being designed as a corner system of board analysis in accepting or rejecting a particular polar frequency to the industrial control system. This will be a typical board plot. You can see the board plot looks like this. You can see the x-axis, and you can also view the y-axis gain of the system. This is all about the theoretical concepts of the control system, which is very vital in understanding what the control system is. And the control system can be classified into feedback control system or non-feedback control system. You can see some feedback control system where there is an adjustment possibility here for some errors. If the errors occur in the system, they can be adjusted. It can be subtracted using subtractors or noise cancelers in the system. They are not big applications as we think, as we study. The noise cancelers or subtractors or error cancelers are simple operational amplifiers. They take two input signals of equal value but opposite polarity. They cancel the polarity by means of the configurations being done in the operational amplifier circuit. The configuration may be a subtractor, or it may be a comparator, and then they yield a value. Either they can yield the threshold value or square input signal to the next system or the unit, or they may yield a cancelled low noise signal which is not arbitrary to the next unit of the system. This is the feedback system with error control. Then we saw the transfer function. What was the need for the transfer function? The transfer function just exhibits the behavior of the particular system. The transfer function is derived from the polynomials of the system and numerical computations, but how they describe the functioning of the system is given by the transfer system plot. This is called as the transfer system plot. It is going to give us how the system actually behaves for a transfer function, and how the system behaves is directly known to us by seeing this plot. We saw the system frequency response, which also requires some transformation, which is called as a Laplace transform. We have different transforms for different subjects. In the control systems, we use the Laplace transform, but in the radio applications, we use Fourier transform, which is highly complex compared to the Laplace transform. Laplace transform converts the polynomial into what is called as a time domain, which is real time Laplace transform continuation. So as and when the signal enters the particular system, how the signal is going to be modified by the system, or how the system behaves to the particular signal, is being derived by Laplace transform. Laplace transform gives output as one value. It is not sufficient. Hence, we require computational tools like MATLAB, which may interpolate what is given for a set of input signals or set of input data to the system, and how the system handles the set of input data or the set of data transformed into the signal. And we want to close the concepts related to the control system, and these concepts are very difficult to understand at the first attempt unless and until there is a practice in terms of numerical computation or practice using hand-derived mathematical analysis. Thank you very much for listening.